Welcome back, Chem 151 students, for week 8. This week we're going to be talking about chapter 23, which has to do with transition elements and coordination compounds made from those transition metals. So the picture here is a picture of the Statue of Liberty. The top one is not a real picture, it's a recreation of what the Statue of Liberty would have looked like when it first arrived in America. It's made of copper. So it will look brown like a copper penny, but now it has this green color due to the formation of transition metal compounds containing copper on the outside. Transition metal chemistry is really interesting because it has to do a lot with the color of things, like paints. A lot of paints use transition metal compounds to achieve a particular color, and so that makes transition metal chemistry really interesting, and there are other reasons why it's interesting as well. So let's start to talk about them. First, a little review of what is a transition metal. So the transition metals are those that are in this orange square here. These are referred to as the D block elements of the transition metals. Down here, the F block fits actually right in between here, the S block elements and the D block elements. These are the inner transition metals. We won't be focusing as much on these, but their presence does have an impact on the rest of these transition metals, so we will talk about them, that effect a little bit. So the most important thing is transition metals. As you can see, we called this the D block because this represents the introduction of D electrons into D orbitals in atoms. So transition metals have D electrons. And the way we determine those is based on the position on the periodic table. So this is just a little reminder here of how to write electron configurations. Here we have the electron configuration for scandium, and so I'm just going to show how we arrive at that. Generally, for writing the electron configurations, we can use the periodic table. In general, for the main group elements, the S block and the P block, the energy levels in which the electrons go can be indicated by the row number here, or the period number, as they're called, 1, 2, 3, 4, 5, 6, 7. And for S and P orbitals, the energy level, or N, is going to be equal to the period number. And so here, for example, the electrons going into the lithium atom in its S orbital here, this is the S block, going into the second energy level, or shell. For D orbitals, it's going to be the period number -1, and for F orbitals, it's going to be the period number -2. And other than that, to write an electron configuration, we simply read the periodic table. So let's do a simple one like carbon. If we're doing carbon, we can, or let's do like silicon right here. If we're doing silicon, the way we'd read this is we'd start at the top left of the periodic table, and we'd write a 1 for being in the first row here. So this is going to be for silicon. And then we say S because as we're starting on the left here, we're in the S block, these first two columns here. So that the first electrons are going to be going in the 1s orbital. And for the purposes of writing the electron configurations, helium kind of belongs next to hydrogen because the first energy level only has an s orbital. So you can kind of picture, for this purpose, helium being right here in this spot. So we count across the first s area here, 1, 2. That s orbital can fit 2 electrons. Then we're completely done with the first row. We drop down to the second row, and we write this is a 2 here. We write 2 because we're on the second row. We're still in the S area. We're starting with lithium here. We're going to write an S, and then we write how many electrons to go across that S area. 1, 2. How many boxes, basically. And this represents 2 electrons going into the 2s orbital. And at that point, the 2s orbital is full. So we travel across this empty space here to where we get to boron here. And since we're still in the second row, we'd write a 2 again. However, we're no longer in the S area over on the left. We're in the P block over on the right. So instead of writing an S, we'll write that P electrons are going, or electrons are going to P orbitals. And then we count our way across 1, 2, 3, 4, 5, and 6. There are 6 spaces across, which indicates 6 spaces for electrons. And that's because if we're looking at the relative energies here, it always goes that the 1s is the lowest in energy, then the 2s, and then next is the 2p. And a set of p orbitals are degenerate, meaning they have all the same energy, and there are 3 of them. And each of these orbitals can fit 2 electrons. And so what I'm writing with the electron configuration is a shorthand version of what you see here, the energy diagram. Next, we've completely crossed the P area and we're at the end of the second row. So just like we're reading a book, we drop down to the third row and we write a 3. 3. And since we're in the S area, 3, we write S here. And now we count across the S area, 1, 2 spaces, so those 2 electrons fit in that S area. And then we travel across this empty space here. We're still in the third row, so we write 3, but this time we're in the P area, so we write P. And then we count till we get to the element or the atom we were looking for, which is silicon. So we count in 1, 2 spaces. So we write 3p2. And that's a total of 14 electrons because a silicon atom has 14 electrons. There are 2 in the 1s, 2 in the 2s, so that's 4, plus 6 more in the 2p, that's 10, plus 2 more in the 3s, that's 12, plus 2 more in the 3p, that's 14. Now there is a shorthand way you can do this. You can do a shorthand for all of the stuff that is in the all of the core electrons, as they call them. So the core electrons are those that are at the lowest not the highest energy level. So they're underneath the highest energy level, which is level 3 here. And to make this shortcut here, you can write down in brackets here the transition or the noble gas that has that electron configuration. In this case, it's neon. So neon goes all the way up to the second row, the end of the p orbitals. So that's neon right here. This is its electron configuration. Then you can simply write the remainder that comes after that that noble gas, which would be 3s2, 3p2. Write the rest. 3s2, 3p2. And so either of those is acceptable. Often this is used. I'm going to use the shortcut way from now on because it's just easier. So you just find the noble gas that's above, and then you continue reading the periodic table like it's a book. Now we haven't gotten into the D block yet, but when we do, the energy level for the D block is going to be the period number -1. Let's do scandium that was shown on the next slide. So if we're doing scandium next, scandium. So scandium, I'm just going to use the shorthand method. So since scandium is right here in the 4th row, I'm going to go up to the noble gas in the 3rd row and find it. And that's argon. So I'm going to write bracket argon here. Bracket argon. And then I'm going to continue after that. So once I get to the end of the 3rd row here where argon, I'm in the 4th row S area. So I write 4s, and then I count across the S area. 1, 2, 4s2. And then now the orange area I'm entering is the D area. So for my energy level, since it's the D area, I write the period number -1. So the period is 4. So I'm going to write 4 minus 1, which is 3. And now I'm talking about electrons that are going in the 3rd energy level D orbital. Since scandium is only 1 block in here, it's just the first electron, 1. Okay. And as we go across this area, we're going to have more and more electrons filling this up. If we get all the way to the end with zinc here, it will be argon 4s2, and then 3d 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. Now, with the f orbitals, I don't tend to focus too much on those electron configurations for the f orbitals. You know, they're kind of you know, unusual elements for the most part. Many of them are radioactive and unstable. However, let's try one here. Let's try one. Let's go for we're gonna go for one that includes these. So let's go for like gold right here. Let's write the electron configuration for gold. And so again, we'll go up to the row above and write its noble gas, which is xenon here, and put that in brackets. So we'll do bracket xenon. And then we're on the 6th row here, and we're going to start by filling in s electrons. And so this will be 6s, and it's 2 across. 1, 2. Okay. Then this black line here means that actually the inner transition, or F block, fits right in between here. Okay, so this is going to represent the filling of F electrons. And so we'd say, instead of 6 now, we're going to say the period number -2. Since we're in the F, it'll be the period number -2 right here. So we'll say 4F. And then we count it across. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. F orbitals can fit 14 electrons because they come in sets of 7 that are degenerate. Kind of like the 2 P's here that come in sets of 3 that are degenerate, but they have more. And finally, we're going to count now into the d orbitals here. 1, 2, 3, 4, 5, 6, 7, 8, 9. 3d9. Now, this in fact is not the correct electron configuration for gold, because as I'm going to show you, there are exceptions for group 6 here and group 11. In fact, if I correctly write the electron configuration, what's going to happen in these guys for chromium and molybdenum and for copper, silver, and gold is that because this d orbital is almost full, and the s orbital, as you put more and more electrons in, they become higher and higher in energy. In fact, one of these s electrons is going to jump up to the d, so there's only going to be one s electron. There's going to be 10 d electrons. And so that's going to be a little bit of an exception there, and that's what I'm going to mention on the next slide. So that's the way in which you determine what electrons are in what orbitals and write the electron configurations. Again, the d block here represents the filling of d electrons. Watch out for exceptions in group 6 and group 11, chromium and molybdenum for group 6, and copper, silver, and gold for group 11. Here's the same type of situation for copper as we saw for gold, except it's filling the 3d orbital instead of the 5d. However, it's the same thing. When it's almost full, this is in fact not going to be the electron configuration where there are 9 electrons in the d orbital and 2 in the 4s. Instead, because these are so close in energy, one's going to jump up, or basically fall down. These are so close in energy that 3d is slightly less, and there's a special stability here with this full shell versus an almost full one. So the electron moves over here and occupies the 3d orbital, filling it up, and we have 1 in the 4s. And so that's true for group 11. It's also true for group 6, where for group 6 you might expect them to have a 4s2 3d4 configuration. However, this being very, very close to a half full shell, and these two orbitals being very close in energy, the electron here will unpair in the 4s and instead half fill the 3d orbitals. So watch out for those exceptions in group 6 and group 11. Finally, when these transition metals make ions, as I said, these s orbitals and these d orbitals are very, very close in energy. And as you begin to add more and more electrons to the d orbitals, the relative energies start to shift to where the 4s is actually higher in energy than the 3d after it's been filled up. And so the result is that if you have a atom like iron here, whose electron configuration has 4s2 3d6, any electrons that you remove to make an ion will first come from the s orbital. So that's something to keep in mind. So if we're making iron 2+, that happens because it has lost 2 electrons. And those 2 electrons will come out of the 4s orbital first before they come out of the 3d. Then the third and final electron will come out of the 3d orbital. And remember, when you're removing it, you want to remove the one that is paired first. That electron is higher in energy. The electrons do repel each other, so if they're paired, there's a slight repulsion in that orbital, and so that's the electron that would be removed, leaving 5 unpaired electrons in the d orbital. And unpaired electrons are going to become very important here. A question I'll ask you very regularly is how many unpaired electrons, because that's going to affect the magnetic properties of the element. You may know iron as being very magnetic, or we call it paramagnetic. This is due to the fact that it has 5 unpaired electrons in the 3d orbital. So this is a summary here of a lot of different properties for the period 4 transition metals. So you can see their electron configurations here, including those for the ions, their electrical conductivity, melting points. So you'll see an interesting pattern here. The melting points are rising, and then they fall off, and then they fall very much off at the end. That's something interesting we're going to look at in a moment. We're also going to look at the densities of these metals. So again, you're going to see this interesting trend where the density is rising. It slightly falls off here at the end. And then atomic radius is going to be something that's interesting not only horizontally across the periodic table, but also vertically. And so you're going to see here atomic radius kind of going opposite here to the density, dipping, and then rising here at the end. So let's talk about each of these properties individually. In terms of metallic, so what it means for a metal to be metallic, be more metallic, is metals are metallic because they have a weak grip on their electrons. That's what makes a metal a metal. And nonmetals are nonmetals because they pull very strongly on their electrons. And so we, in previous classes, you've talked about the general pattern of periodic trends on the periodic table. Basically, up at the top right, these nonmetals have very, very strong pull on electrons. So this is strong electron pull up here. And this is due to the fact that as you go left to right, you're adding more and more protons, which are attracting the electrons inward. However, those electrons are not getting any farther away from the nucleus. However, as you go down the periodic table, the electrons are farther and farther away from the nucleus. So you end up with a very weak electron pulls on the ends, and that's just generally speaking. But those trends do kind of differ in the middle of the transition metals. So that's why we're kind of talking about those specifically now. And so you'll see the normal pattern like that you would expect is more metallic on the bottom left, less metallic on the top right. But you see there are some differences here. In general, you can see that overall, yes, they are less metallic near the far right, but there's some kind of, it's not a smooth like downward trend here. The scandium is less metallic than the titanium, which is less metallic than the vanadium. But then the manganese here drops in metallicness, and the zinc is very, very low. And you can see this is true. You have this dipping here on both of these. And this has precisely to do with the fact that for magnesium and technetium here, these represent half-full electron shells. And as we said on the last slide here, there's a special stability to half-full electron shells. And so you can see the result of that. The electrons are less likely to move, to be mobile, which makes these less metallic. That's also true on the very end here. It's even more true. And it's true for those that tend to the exception column here as well, where the s electron tends to go and fill the d orbital. Because there's a special stability to that full d orbital, these electrons are much less likely to move, and so that means less metallic properties. And this is especially true for mercury. The metallic bonding is very weak between mercury atoms for this reason, among other reasons, which contributes to the fact that mercury is a liquid at room temperature. Another thing you'll notice here, which is going to be relevant, is that there's a much bigger jump in differences of properties between the first transition metal series and the second versus the second and the third, and we're going to talk about why that is. And this has everything to do with atomic radius here. So that pull on electrons I was referring to, that's also called Z effective, or effective nuclear charge. And again, it's strong at the top right of the periodic table, weak at the bottom left. And so we expect here, because Z effective is increasing as we go left to right, that we would see a stronger and stronger pull of electrons, pulling those electrons inward, leading to smaller and smaller radii as we go left to right on the periodic table. In fact, we see that at the beginning of the series, but near the end, the radii widen out again, right? And this is again due to this full electron shell here. So when we have this full electron shell, essentially this is a more stable atom, and the whole pull relaxes a little bit. And so you get a little bit of an increase here in atomic radius. But what's really even more interesting than that is the fact that you get a pretty significant bump increase in radius as you go from the first series to the second series here of transition metals. However, you get almost no bump. Notice a lot of these have exactly the same or very close to the same atomic radius as you go from the second series to the third series. This is due to what's known as the lanthanide contraction. And I'll explain to you what the lanthanide contraction is. The lanthanide contraction is this. If you look at the third series, just going back to the periodic table here, you're going to see that for the third series, it's different from the first and the second series. So this being the first series here, this being the second. In the third, before we fill up the d orbitals, we have a whole bunch of extra elements that add a whole bunch of additional protons and electrons before we ever start filling the d orbitals. And the result is that this element here starts with 71 for its atomic number, 71 protons. So here, like from here to here, you only have a jump of 11 in terms of atomic number, from scandium to deuterium. However, from 39 to 71 here, that's a huge jump. We're talking about, was 22, or 32 rather, 32 versus, just right here, 18. So a huge jump because of the introduction of these guys in between here. And so the result is that when you get to the third series here, you've got a lot more protons because we had the filling of all of these protons in right here. And so you can see that between the second series and the third series, the radius does not jump very much because of the addition of many, many protons, leading to a much stronger pull, which results in not a significant increase in atomic radii from this fifth period to the sixth one, basically, or the second series in the transition metals versus the third. This is due to the lanthanide contraction. So the lanthanide contraction, the radii actually decrease as we go from, or stay close to the same here as we go from the second transition metal series to the third, or from the fifth period to the sixth. And then you've got the same kind of pattern here you saw with atomic radii and metallic property with the main group transition metal elements. The main transition metal elements is that there's a little bit of there's a bump here in radius for the stable half full F, and then for the full, which is the YB here, which you don't have to remember that. What I want you to know is that for the 5th period and the 6th period, the atomic radii do not change significantly due to the lanthanide contraction, meaning because of the significantly additional protons due to the filling of the lanthanides here, you have a stronger pull. 4F subshell fills, so Z effective increases significantly. Finally, in terms of densities, the densities are going to go opposite essentially to the radii. So we saw the radii were decreasing as we went to the middle, then increasing at the end. So the densities go up as you go towards the middle, and then they dive down a little bit at the end. It's the same property. And you can see here that because the radii don't increase very much between the 5th period and the 6th period, so this is period 4, 5, and 6, the density of the elements, the transition metals, increases very, very much between the 5th and the 6th period, because although there are many, many more protons and electrons, the atoms are not significantly larger in size. This is also due to that lanthanide contraction. So the main point of all these properties here was to demonstrate to you this lanthanide contraction and its effects. Well, let's practice with this. What is the electron configuration for molybdenum? So what I'm going to do is I'm going to open up a regular old periodic table so that I don't have to go back and forth here. Oh, whoopsie. I didn't have it in that folder. I know I have it over here. Okay, so we've got molybdenum. So molybdenum is right here. Okay. And so to write the electron configuration for molybdenum, we would go to the row right above, look for the noble gas, it's krypton, so we write brackets krypton. And then we read underneath, so we're in the 5th period. This is the S area here, so we'll say 5S2. And then we'll count in 1, 2, 3, 4. And this is going to be 4. Since it's a D, we do the row number -1, D4. But watch out. This is one of the exceptions because we have a almost half full D subshell. So instead, this is going to be 5S1, 4D5. And that will be the actual electron configuration. Remember that in row 6 here, in group 6, chromium and molybdenum are exceptions, so the 1 electron goes up to the 4D here and half fills it, and then copper, silver, and gold are exceptions here as well. Okay, now going back to the slide. So we got that one. What is the electron configuration for vanadium 3+? Okay, vanadium 3+. So let's get it for vanadium first. So vanadium, it's going to be the noble gas right above vanadium. Vanadium's here, so we use the noble gas argon. And then we'll be in the 4th row, S area, 2 across, so we say 4S2. And then we count into vanadium. It's going to be 3D, since we do the row number -1. 1, 2, 3, 3D3. So that's vanadium. Now if we want vanadium 3+, vanadium 3+, not liking me too much writing there, so I'm just going to copy this over. I wonder if I can copy it to the slides. That would be cool. No. So we got for vanadium, it was argon 4s2 3d3. Now we're making an ion, so for the ion vanadium 3 plus, it's going to be argon, and then we're going to remove electrons from the s orbitals first. So we'll move 2 from here and then 1 from the 3d orbital. So it'll be argon 3d2. Finally, rate these elements, palladium, nickel, and silver, in terms of increasing atomic radius. So these guys, for atomic radius, they're right on the end here, nickel, palladium, silver. So this is where you are to remember, radii get bigger as you go down because you just got more stuff, except they don't get very much bigger from period 5 to period 6. So nickel is going to be smaller than palladium, but palladium is going to be smaller than silver because the radii go up near the end there. So our answer is going to be that nickel is smaller than palladium, which is smaller than silver. Nickel has a lesser radius than palladium, which is lesser than silver. So that's how we write down electron configurations for metals, and that's a little bit for transition metals, and that's a little bit of the differences in periodic trends from transition metals versus main group elements that you learned about earlier. There are a little bit of differences, mainly having to do with the fact that there's this special stability, especially to completely full D subshells and half full as well. Okay. So now we're going to go into a little bit about why we're going to be learning about transition metals. So transition metals have a lot of interesting chemistry, and among the most interesting things is that most transition metals are variable charge. They can have a variety of charges. So here you can see this for manganese. So manganese is having an oxidation state of a charge here of +2 all the way up to +7. And you can see that the result is that the manganese compounds that are formed have a great variety of colors. And so that's the next thing we're really going to focus on a lot in this chapter, is the different color compounds that can be formed from transition metals. They make quite a variety of compounds. We're also going to now talk about the chemistry that has to do with them changing their oxidation number or their charge. You're not going to have to memorize any of that. It's just kind of something interesting to talk about. After that, though, we're going to be focusing on the compounds that are made with these transition metals and the colors that result and why those colors result. But you can see that depending on the oxidation state or the charge of the manganese, whether it's 2, 3, 4, 6, or 7, you're going to have a variety of different colors. It's also going to depend on what other components of the compound are there. So in terms of what oxidation state that these various elements can have, the red dots here, these are all for the period 4 transition metals, but they apply to the transition metals underneath as well, more or less. What you'll see here in terms of pattern, and this is very important that you understand this pattern here. First of all, look at the red dots. So the red dots are the most important. Those are the most common transition states. And you can see that, the most common oxidation states. You can see that the most common oxidation state for scandium is +3. And this is because a scandium atom has 2 electrons in the 4s orbital and 1 in the 3d. So if it loses all those electrons, it's going to be losing 3 electrons, which makes a +3 ion. For the titanium, it's going to be 4s2 3d2 before it's an ion, so it has up to 4 electrons to lose. And so most commonly it will lose all 4 and make +4 ion. It can also make +3 by losing some of these and +2 ions, but +4 is the most common. And if we move forward, vanadium will have 5 electrons in its s and d orbital, so it can make an oxidation state up to +5. For chromium, it'll have 6 available, so it can make an oxidation state up to +6. For manganese, it's going to be 4s2 3d5. So there are up to 7 electrons available to lose. And so if it loses all 7, it makes a +7 ion. But it can lose many other in-between amounts of electrons. It could lose 2. And as you can see, 2 seems to be the most common, especially as we get past the middle. So once we get past the middle, so remember that this half-full subshell has a special stability to it. It takes additional energy to break this up and to remove the electrons. And so what happens is that once you get past this middle, this half-full subshell, it turns out that breaking into that and breaking that up becomes increasingly difficult and increasingly less common. So you can see that for iron and cobalt, +2 and +3 ions are common. We can explain this fairly well for iron because it would be a 4s2 3d6. And so if it's losing 2, that's losing those 4s. And if it's losing 1 more, it's leaving 5 in the 3d, which is the half-full subshell. And so that's not too surprising that +2 and +3 are the most common oxidation states. For cobalt, it's also +2, +3. Then for nickel, it's just about always +2. For copper, very interestingly, it's the only one with a +1 oxidation state that's very common. And here's why. It's because it's that exception where we had 4s1 3d10. So here we have the full D subshell, which is particularly stable. So to make a +1 ion, all you'd have to lose is the 1 in the 4s, leaving that full 3D subshell. So that's what makes copper 1 ion particularly stable. And then zinc will basically only make +2 because, of course, it has 4s2 3d10. And if it's making a +2 ion, it's just going to be losing the 2 right here. And so that would, again, leave the full D subshell. So once you pass the midway point here, where the d orbital is half full, you stop getting these larger and larger charges. So you don't have to memorize every detail of this. I want you to be aware of the highest possible oxidation state and the reason for that, and also the reason why the oxidation states drop off after we get up to the group 7b, or the manganese group here. It's because of that half full subshell. And then also, you'd be aware that copper can make +1, and the reason why it's because of this exception. So the general trend here is what you should be aware of and should be able to explain. So this is an explanation for kind of what's going on. For group 8b, the loss or sharing of all valence electrons is energetically prohibited because we have increasing values of Z effective. There's more and more protons, so it's harder to pull the electrons off. And also, we have that half-full subshell, which also contributes to that stability. So removing extra electrons is just costs too much energy. Now, that is not to say that you can have reactions. For example, this one here, where the oxidation states change. Okay, and we're going to talk about a few of those now. Just a few general examples. You don't have to memorize any of these reactions. These are just kind of showing you some of the important transition metal chemistry that we use a lot in industry and just observing the way things happen. So what we're going to start to talk about soon are transition metal complexes. So if you have a chromium ion, chromium +2, that is in water, what happens is that the chromium is positive. So the negative side of the water is quite attracted to that positive ion. So water ions tend to bond themselves in a certain way, in what's known as a coordinate covalent bond. We'll talk about those as we go on. And it makes this what's known as a transition metal complex with water. And the color of that complex is blue. That color can be different. It will be different if you have a different charge to the ion. So here the charge on the ion is chromium 3 because it has differing ligands here. We're going to call those ligands, which are chloride ions. And the result is that the chromium 3 has a different color than the chromium +2. And this is very important because chromium the name of it comes from the Latin chroma for color here. So chromium means colorful. And so even the ancients knew that chromium compounds are very colorful. They didn't know why. But you can see that there will be a lot of different paints that have chromium. If you go to the paint store, like the art store, it'll be like chromium blue or chromium green. And this is because the differing chromium compounds with differing charges on the chromium ion will result in different colors. And those chromium compounds are what give color to the paints that you buy or the paints on, you know, a work of art. And so this is very important to color chemistry. Another interesting fact about chromium is that, and some other transition metals, is we're going to see that they're what are known as amphoteric, meaning they can act as either acids or bases. So a chromium hydroxide, for example, is clearly basic because it's a hydroxide. But surprisingly, it's also acidic. It can react with hydroxide ions to form a complex ion that has one additional hydroxide. And so the chemistry behind this and the way in which this happens is something that's going to be the topic of our chapter as we move forward. And there are a number of transition metals that are amphoteric in this fashion. And we're going to use that property actually later on. When we get into experiment 13, we can use the fact that a metal is amphoteric to change its solubility, because ions are generally very soluble in water. But you're probably aware from your solubility rules that neutral hydroxides are not. And so if we have a chromium 3 ion here, and this has water molecules attached, but it's chromium positive 3 ion, it's going to be quite soluble in water. However, if we react it with a base and make the neutral chromium hydroxide, it will precipitate out. But if we add in additional hydroxide, we can actually make the chromium into a new compound that has an additional hydroxide, and that actually has a different color. And so this amphoteric property of these transition metal cations is going to be pretty important for helping us to separate them. And that's what experiment 13 is going to be all about. It's going to be about basically empirical processes, meaning just based on data and observations that are used for having certain metals precipitate and can be collected as solids while others do not, and you can collect them separately. And that's a means by which we can separate the different ions. And so this fact that chromium is amphoteric will be quite useful for that. Again, chromium, the name comes from the fact that the different compounds of chromium have all kinds of different colors. In chromate ion and dichromate ion, the oxidation state of chromium is +6. So you get this yellow or orangish color depending on the ion here. And dichromate happens to be a very powerful oxidizing agent. And so when we want to oxidize things, we often use chromate ion or dichromate due to the fact that the chromium is such high oxidation state here, it itself can be reduced. So something that is reduced is also called an oxidizing agent. And so as you can see here, this in fact has a +6 oxidation state, and at the end it has a +3. And so it itself was reduced and thus was acting as an oxidizing agent. Here is a picture of a chromate ion being exposed to acid and turned into dichromate ion. And so you get yellow color for the chromate ion, a kind of darker orange color for the dichromate ion. So again, chromium, depending on the compounds it's a part of or its oxidation state, can have a variety of different colors, which contributes to its usage in paint and the name of it. Iron. So iron also will react with acids here, produce iron ion. It will be oxidized here. And iron is actually oxidized in air to iron 3 ion, which ultimately produces rust. And so iron rusts in this fashion. Iron, again, like most neutral hydroxides, will precipitate as a hydroxide, which again is something that's very useful to us. However, unlike the chromium, the iron is not amphoteric. It will not accept another hydroxide being attached to it to make an ion, a negative ion. And so that is a useful property. If we had both iron and chromium ions in solution, we could make the solution very basic, and the chromium would dissolve as an ion. However, the iron would not, and so it would stay as a solid, and we could separate it out. Finally, copper. Copper generally comes in the form of copper oxides or copper sulfides in the ground. And so it can be, if we have copper sulfide, there are industrial processes to separate the pure copper. The most common processes are electrochemical processes, and we'll talk about those specifically at the very end of the class when we talk about electrochemistry. But what's something that's really interesting about copper is that if it's outside in the air with oxygen, CO2, and water, it will react, and if it's finally there's often some acid in the rain, it will finally react with that acid in the rain and form what's known as a green patina. And that green patina is what you saw on the Statue of Liberty. That's why the Statue of Liberty is green, or this copper statue of a lion is green due to that green patina. It's actually underneath, if you were to scratch it, underneath is the brown copper, but on the surface is this green patina. And so that's some interesting transition metal chemistry there, and some of the interesting reasons why we're studying this transition metal chemistry. Obviously, there's a lot of complexity there, but we're just going to be focusing a lot on the color aspects, and so we'll begin to talk about that in the next lecture. We're going to talk about coordination compounds, how they're formed, and how to name them. And so that will be our lecture coming up next, and I'll see you for that second lecture.